Let's fix this. In this video, we'll show you how you can write a dynamic programming solution by only thinking about the problem through the lens of recursion. And we'll also cover a technique which you can apply to every dynamic programming problem. Let's start by talking about a pretty popular problem, climbing stairs, where you're given a staircase with n steps and your goal is to find the number of ways to reach the nth step, given you can only climb this staircase 1 or 2 steps at a time. Now, this is a dynamic programming problem, but let's just forget about that for now. Let's just straight away think about how we get to the last step. We know that given we can only climb this staircase 1 or 2 steps at a time, we've either landed to step n from step n minus 1 or from step n minus 2. So since we're looking for the number of ways to get to step n, that's essentially the same as asking how many ways did we get to step n minus 1 and how many ways did we get to step n minus 2, giving us this formula. This doesn't just apply to step n, by the way. We could actually get to any step using this same formula. So if we just replace n with an arbitrary step I, the formula still follows that the number of ways to get to step I is equal to the number of ways you get to the 2 steps below it. This is a recurrence relation, which you can just think about as a recursive formula, where we identify the solution to the main problem by getting the solutions to 2 of its subproblems. Of course, with any good recursive formula, we'll need some base cases to make sure the recursive process doesn't continue infinitely, creating a black hole and sending us to the 4th dimension. Think about base cases as the simplest version of the problem, that we can't break down into further subproblems. A staircase of size 1 is a good example of this, where we know there's only one way to get to the nth step. Similarly, a staircase with 2 steps, we know that there's only 2 ways to get to that 2nd step. Quick tip, by the way, another way to check that you've covered all your base cases is just to check the recurrence relation. In particular, check the parameters and make sure that they can't become any values that don't make sense in the context of the problem. For example, in this problem, it doesn't make sense to have a staircase with negative steps. So we can make sure we don't consider any staircases that have a fewer number of steps than that. Consider a staircase of size 6, and let's expand this recurrence relation so we see the entire recursive tree. Notice the leaves of this tree are base cases because we don't want to go any lower than that. Take a look at something interesting here. Some of these subproblems are solved multiple times. Observe subproblem 4, for example. It gets solved twice. This is a waste of time. We don't want to be solving the same subproblem multiple times. It's not like we're expecting a different answer on the 2nd or 3rd time. We know what the answer is. It's consistent. Okay, but what if we only solved it once? What if we stored the answer the first time we solved it and then just reused that answer whenever that same subproblem shows up again? This is known as memoization. All memoization does is just store the answer to subproblems so that they can be reused later. And this one technique reduces this tree to this and this tree to this. The power of memoization is now in your hands. Okay, let's see how this works with the recurrence relation. So first off, to reuse the solution to this problem, we need to store it in our memo array. Though if you think about it, these subproblems would have also been stored in the memo array after they were solved. So now we have this kind of array relationship. Hang on. No, yeah, there it is. Yeah, I'm not joking. That's all you have to do. Once you've marked in the memo table, you just need to yoink out the memo and slap on the DP and there you have it. Just remember that DPI and MemoI are both designed to store the answer to subproblem I. As for the base cases, they're identical to before. This time we're just storing them in an array. And to populate the rest of the array, we just need to do it in reverse. So if you think about the recursive solution, which is a top-down solution, where we start with the main problem and go all the way down to the base cases. Whereas DP solutions follow a bottom-up approach, where we start with the base cases and then go all the way up to the main problem. So that's how that process works. If you want to see what it looks like on some tougher problems, then give this a read, link in description. So a burning question you may have is, how can I even tell if a problem can be solved using DP? 2 things, optimal substructure and overlapping subproblems. Optimal substructure just means the best solution of this problem is obtained from the best solution of its subproblems, but the real kicker is the other one. Overlapping subproblems just means a subproblem could get solved multiple times, and this is really what DP is all about. It's taking a problem that has subproblems and ensuring each of those gets solved at most once, avoiding duplicate work. In other words, DP is an optimization strategy, so we're looking for words like maximum or minimum or longest and shortest, since these words indicate the problem may be an optimization problem and perhaps could be solved using DP. And yeah, that's it. Subscribe for some good luck on your next interview.